still unclear about what we need to read. Yes, when that says through chapter 2 through 2.5. 2.5, and in the case of, and by the way, that's pretty much the whole chapter. I think there's 2.6 is, you know, like question and answer kind of stuff, problems. So that's pretty much the whole chapter. You cannot find 6.5 in chapter 6. Let me check. I got a book here. Chapter 6. Chapter 666. Well, I have a chapter 6.5. It covers, so I don't understand that one. I would think you might have the wrong book or something, like as Steve said. So on the homework, if I change the mode of a table, does it automatically just, I don't know. And let's get started then. So through 6.5, we'll go back and finish a lot of what's in the final section in chapter 6 is about transactions, and we're just not doing transactions just yet. There's a whole lot of areas there. We're going to be reading some about constraints too. I might have to assign that next. I'll look into where your next assignment is. But no, I don't think it's designed to be read, and certainly not memorized. It's there to talk about the same kind of concepts, which that's really what we're going for here. Okay, let me get it a little bit started. So I have some announcements to get started. So homework 2 has been released. We are setting up homework 2 on Gradescope using these auto grader features. So instead of being graded by a human, you're going to be graded by a human machine, a human programmed machine. We'll see how that goes. You should be able to tackle the entire homework by next week, so I'm hoping that you can. And it's lots of practice with joins. It's still basically pretty simple, but lots of joins. Just a few announcements for students who enrolled late, because we loosened up the enrollment. I think we added about 10 or 12. I'm not exactly sure the correct number, but what happens is you get enrolled, but you're not enrolled automatically into Gradescope. We've been doing that manually, and we need your UW email. Not everybody uses UW email. They use their own private Gmail often, which is fine. But we need your UW email because they are linked, and your student number, and then we can add you. So anybody that's not there, we've probably gotten them all through the weekend and through today, but if there's anybody missing that. As far as the discussion board is concerned, you'll get a notice from IT. That is something they do, and then it allows you to sign on to ED. I think everybody's gone through that, but okay, if you haven't, talk to us or we'll refer you to the help desk. And those of you that enrolled late, your homework due date is extended to Wednesday at midnight. If you, I would caution you though, you did join late, but please try to catch up and not fall behind, because we got the next homework being released right behind it. If anybody else is looking for an extension for various reasons, let us know. We're going to be as flexible as we can here. But again, the problem is not falling behind. Okay. Anybody have questions about that? Yeah, I think you can. I saw that question about that. Okay, so let me just make a few sort of meta comments about what I see as doing in the class. My feeling that learning something like SQL, a programming language, is best accomplished through practice. So one thing for me to talk about, you know, and lecture about it, or you to read it in the book, the thing that you're going to learn is learning about it through practice. And my advice is you not try to memorize all the rules of the language, some of which are fairly arcane. It has a basic logic structure, which I'm trying to discuss. But when you're learning it, I don't think the idea is to memorize all this stuff and ask how deep to read the book. It's to understand it enough to use it. And when we do an exam. It's going to be checking your knowledge, your ability to write good SQL to answer, to answer a problem. I consider the SQL syntax checker to be my friend. I don't remember the syntax, exact syntax of any programming language that I've learned over my career. And, you try it, and the syntax checker will tell you when you have a problem. Some are better than others. Some of the errors are a little obscure. There is help. There's help. There's help everywhere. They're usually documented. My advice is to work iteratively. You learn through trial and error, and particularly in this kind of thing, you get a little piece of your SQL working, and then you add another piece and another piece. Out on ED, I was tempted to answer some of the questions that people raised on the discussion board about how this particular SQL statement works. But, my instinct is to think that's the wrong question. If you want to know how it works, try it. And I don't always know how it works either. And that's how I figure it out. I run it against the database and I see for myself. One final note, and I'm going to mention this over and over. We're going to see this. Relational algebra is an algebra. It's not an algebra involving formulas that you're familiar. We were taught back in middle school and high school. But it is an algebra. It's based on set theories and set operations, and it is an algebra. It's a group in mathematical terms. And the one aspect of algebra, of it being an algebra, is similar to the algebra that you learn, is that there are often many ways to compute the same answer. Just because the teacher did it this way doesn't mean that your answer, which was arrived at using a different sequence of steps, is the wrong answer. In fact, there are many ways to compute the correct answer, and we'll consider any answer that produces the correct result set to be a good answer. The only problem sometimes that you get into, I'm going to see some of that as we go through examples, we'll kind of look at edge cases. Sometimes you'll compute the correct answer, but your SQL isn't general enough to solve the problem. It'll only work because of the limited subset of data that you exercised it in. And that's a tricky area. That's a tricky area in all of computing, where we can't always guarantee correctness, and we can't prove correctness because of what I mentioned earlier last week. The halting problem, basically, that we find in computability in our languages. So it isn't always possible to understand whether something is going to work or not until you try it. And there's lots of ways to get to the same answer. Okay, I don't want to belate that, but the fact is, the algebra is an algebra, and that's going to keep coming up. Okay, let's review what we did the last time. What we've learned in the last couple of sessions is about modeling tables that are multiple tables that are part of the same database, and we looked at keys to these relations. Unique keys that identify a given tuple are known as primary keys. And we looked at relationships being modeled using foreign keys, which is a pointer in one table back to the primary key of another table. The kind of relationship is implied. You have to kind of know that from the semantics of it. We'll get into it, of the actual data, but that's how we do relationships. You can also model relationships explicitly, and sometimes that's useful. We'll get into that. But right now we're trying to keep things simple, and here's our two tables that we've been playing with. Our payroll table and our car registration database. And we saw how they were linked. And when you have data that you need to get from multiple tables because of the relational model, encourages this kind of layout of data. And we'll look into the algebra behind that in a couple of sessions. We execute a join to combine the data from those different tables. Different kind of join. Different kind of joins. You see an inner join, a left join, a right join, or left outer join, or right outer join. Those are kind of Venn diagrams to indicate that. You can do a full join, cross product kind of things. We talked about it in terms of a join and the nested loop semantics, I don't know that semantics is the best term, but that's the one we use. Nested loop algorithm basically that they would use to calculate the product of a join. The most important join, or the most common, is highlighted here. It's called an inner join. In fact, it's so common that it's usually just called a join. Let's talk a little bit more about that from the last time. What we did is we showed you the SQL statement that is used to define a table and define one of the fields as a primary key. And here's the other table with a secondary key, well, a foreign key that references the payroll table. Notice that the field user ID is the same in both tables. The name of the column is the same in both tables, and of course we're going to have to tell the SQL syntax checker about that to disambiguate it. I didn't mention this last time, so I noticed when I was reviewing the slides to create this little summary. When we look at that schematic representation, which is here, notice that this word is underlined. That means it's a primary key. We'll see that convention used over and over. That's a way of indicating a primary key of the relation. I don't think there's any necessarily any easy tag for a for a foreign key like this, but we'll get to that. For now, let's keep going. What we've called that. So that was our foreign key. Whoops. As I said, referencing back to the other kind. Now we saw two ways to write this inner join for this particular in the relational algebra, for this way of computing the answer, to look at those names, the names of people in the database and their cars. And one way was decoded explicitly with the join keyword, and you see join on. And the other way of doing it was not to use the join statement, but to use but have join be implied by having multiple tables referenced in the from clause. So that implies a join. And in this particular case, we have an equijoin. These are the most common joins you'll see. And the particular pattern of this equijoin is that it's a primary key in the table to the left of the join, and it's a foreign key that's equality that is looked at on the other side of the join. So this primary key foreign key relation is the most common. And we also notice that the select then can pull data out of both of the tables that are being joined. Now, a point that we're going to get into further, but for now, just want you to keep in mind, is that these statements are different. But when you see what the SQL does with them, they will generate identical execution plans, not because their SQL is translating one into the other. That's not actually what happens, but it's because the optimizer itself is smart. The optimizer has information about indexes on the tables and basically understands that this is a relationship, that this is a join, and it will in both cases generate the identical execution plan, because it determines that the plan that it comes up with is the most efficient way to get to the data back to you. So that's why they call it an optimizer. It optimizes your query. In effect, what it does is it chooses the best execution, or the faster execution plan among all the possible ways, the forms of solutions to your query, and these would come out the same. We'll get into that a little bit more. It's not because of the same statement or they get translated into the same statement. What really happens is both of them generate plans. Each one of them, if you separated them, the optimizer would pick out a plan that is optimal, and that optimal plan would be the same in this case. Not always the case, but because they're simple enough, they'll turn out to be the same solution. Okay, then we talked about this nested loop semantics as basically a simple enumeration of all the rows in the first table, and then an enumeration of all the rows in the second table for each row in the first table. M times N kind of complexity, sorry. And it's called nested loop semantics because it's a nested loop. Nested loop semantics is useful for understanding how your query, what kind of query is going to result, what kind of results you're going to get. But in fact, it's not the most efficient way to answer most queries, and it's rarely optimal. It's not the one the optimizer is going to choose. If in this example, we saw that we had that the optimizer saw that there was a key there, we were doing an equijoin, it would do what is known as a hash join. I don't want to get into what the details of the hash join are, but it would in effect execute the code that's shown here. What I did was realized when we were doing this on Friday that in that if statement I now show commented out, because that if statement is not necessary given that the foreign key constraint is active. In other words, this user ID has to point to a key field in payroll. Otherwise, the foreign key constraint fails. We'll see how that's handled. We'll give you a reading about constraint. We'll lecture on it. That's coming up. It's coming up pretty soon, probably by next week, hopefully. So I guess I better get your reading ready for you. So in fact, you don't really need this if statement. It's redundant, so you wouldn't have to do it. You know that in fact, the row 1 does have a user ID that equals to row 2's user ID in this case because of the foreign key constraint. That's pretty cool. It makes things, again, much more efficient. Okay, so we talked about that. We'll get into the efficiency stuff and what the optimizer does as we move through the class. Okay, so let's talk about, let me see what kind of questions we're getting. Anything I need to pick up on, Prati, Josh, or you guys think you're handling it? Can we keep going?
Or yeah, I think we're good for now. We can keep going.
Yeah, don't worry about hash tables yet, but that's where we're going with that. Not everybody knows what a hash table is, so we'll get to that in a little bit. We don't need to know it now. I'm just introducing the terminology for now. You don't need to know about it. Okay, so what we're doing is we've started to build our SQL toolbox, and we're starting to answer more complex questions. Now, today, we're looking at aggregates. We're learning how to summarize results. Now, this kind of summarization that you're going to do against query data, you could do inside your program. There's no question of that. It's often, with very large data sets, it's often considered useful to offload that computation onto the database server, have it done inside the database where there's a whole lot of processing power to do it, and a lot of processors that can work on your query in parallel and things of that sort. And then just return the summarized results to you rather than return, which is a lot less traffic over the network. So again, from an overhead perspective or a cost perspective, some people prefer to do their summarization inside the database itself. And we've mentioned that when we talk about SQL, there are basically 6 clauses of a SQL statement. We have seen select, we've seen from that references the tables, those are the relations, and we've seen a where clause. Lots of where clauses, and or, and all kinds of logical operations. Today, we're starting to look at the group by and the having statements. And I mentioned the order by, and that's sort keys and a series of sort keys. And you have to think about them logically. You sort by the one key, and then within the sort key, you might you'll add another sort key, and you'll add another sort key. Numerics sort by numeric order, and you can also sort descending any of these keys. And alphabetics sort in alphabetical order, and you can set languages and a collating sequence and things like that as part of the options of your of your database setup. Okay, so we're looking at the aggregation functions in today's class, the aggregation functions that are available, built into the language. We're looking at the group by and the having clauses in SQL. and I don't think we'll get to it today, something known as the witnessing problem that's a little tricky, but it has to do with grouping and aggregation, as we'll see. So we need summaries of data because we're often trying to make decisions and succinctly convey information, etc. That sounds good. What we've got are some built-in summary functions. We've got the count, just enumerating what's the count. I don't care about the individual results. I just want to know how many people did watch this particular show. Sum, average, max, and min. These are the basic ones that are defined in the standard ANSI language. SQL has undergone a standardization process beginning, I think, around 1985. There have been several different iterations where things have been added to the standard over the years. All of the vendors pay some attention to the SQL standard, and the idea is that if you write ANSI standard SQL, then you can change the underlying database and change out SQLite and put in SQL Server. They're not 100%, they don't adhere 100% to the rules. They'll have some unique things. They may even have some proprietary functions, summary keywords and methods that are built in. For instance, if memory serves, when we start to look at Microsoft SQL Server, we'll see that besides average, it'll also automatically compute standard deviation, I believe, or maybe sum of squares or something like that. Some other function that's relatively easy to compute when you're enumerating through a result set. So, but anyway, these are standard, and you should find them in every SQL compliant database that you work with. Aggregate, this is the first time where we're looking at non-null values, or where it matters whether fields are null or not, and how SQL is going in through its enumeration is how it's going to treat null values starts to become important, as we'll see. Also, another way of doing it, for instance, if you wanted to get sum, or max, or any of those functions, and it would apply to duplicates within the relation, you can also use these aggregate functions with distinct. So I want the count only for distinct anime video views, because and eliminate and not count someone who's watched the same anime over and over again as more than one view. Okay, so if you can count viewers, or you can, by using distinct, or you can count the total number of views. So what the right answer is depends on what question you're asking. You can ask the question both ways in SQL, so it's flexible. What else we got here? If you have a function like count, it's going to work regardless of null values, which sounds good. That's probably what we want on any of some of these other fields. But it turns out when you're using these aggregation functions, and this applies wherever you use some kind of aggregation function, no matter what programming environment you're in, it sometimes matters where and your or how you're doing it. So we're going to look at an example of that. So intuitively, you want to do the aggregation across all the data, but that becomes problematic once there are things like joins. So we'll look at an example of that. And here's our two tables again. And here's the SQL. Select, and here we want to compute the average salary from the payroll table, but we want to do this join. So we're looking at the registration data table as well, and we're doing the join, the equal join on the foreign key and the primary key, basically the primary key, which is a foreign key in the other table. This has some interesting side effects of doing it. Like any other programming language, it does what you tell it to do, and you have to figure out what it is, like debugging it, and like any other language, you have to figure out what it is you told them to do that you got wrong. So let's look at this. It's using the relational algebra, but basically the first thing you're going to do, as we'll look at a little bit further, is you're going to do the join itself. That's the order in which this is executed for you, whether you like it or not. That's the join happens first. This from and where is done first. So the result of that join, if you're with me, is something that looks like this. And that relation, that intermediate result set, if you will, that's the relation that is you're going to do the averaging. You're going to apply the average function to. So that might not be what you want. You wanted the average of these individual salaries, but see, when you did the join, you lost people that didn't have a car. You could have done an outer join to remedy that. And now you have people that have multiple cars in the intermediate relation twice. So arguably, this is probably not what you intended when you wrote this SQL. Because when you take the average of that, you're going to get this number instead of the average of all 4 individual salaries. So this is not wrong logic to SQL. SQL is just going to execute what you told it to do. What's wrong is the way you specified the query. This is probably not the way you intended to compute it. Are there some questions about that? Okay, we're good. Moving on then. This is the relational algebra approach to it. And this is going to turn out to be important because we're going to see the sequence with which this thing is executed. This SQL queries are executed as the clauses are themselves, the order in which the clauses are executed. And why you got into trouble in the previous example is because you didn't realize the order in which this would occur, which is we're going to access payroll P, we're going to access register R, registration relation R, and we're going to then do the join, and then we're going to do the aggregate. So if you don't want that order, you have to specifically specify some other way of computing this. Maybe you don't care about the join here. That would probably help you. In that case, if you just want average salaries. What happens is aggregation, when it's performed, when the aggregation step is performed, it drops data from other attributes. We'll see how that comes up later again, but just try to keep that in mind, that that's what's going to happen as part of aggregation. As you're doing the aggregation, what you're doing, the SQL is doing within a nested loop semantics or some kind of a loop, anything that's not subject to the aggregation is automatically dropped because I wasn't asked to keep it and I don't keep it. And in fact, we'll see with the witnessing problem, I don't know which of multiple items to keep if you didn't specifically ask me to aggregate them while I'm aggregating them. Okay, so questions about that? That's probably not super clear yet, but as you practice this, I'm sure it'll get clearer. So what SQL allows you to specify what groups your query operates over, so you don't have to do the whole table. You can, that's what we were illustrating here, is that you can just calculate the average salary, just watch out what the joins do to it, but for the entire table. But more likely, you're going to aggregate over certain kinds of groupings. And let's look at a grouping, for instance, that would be quite popular in this case, which would be the grouping by job. I want to know not only what the average salary is, but I also want to know the average salary perhaps by job, 2 separate queries to do that. So we can partition the data in effect by job and then report just the summary, the aggregate function, the result of the aggregate function for that grouping of the data. So we would, in this case, we would be calculate the average salary for the TAs and separately and report that as a row in a new relation, a result set. And we could calculate the average salary for the profs and calculate that separately and also report that. So what happens when we aggregate, we're going to produce, instead of a summary kind of thing, when we did this, we're going to produce one row, whoops, went too far. There our result set is a scalar. It's just one column and one row because we've summarized everything up. When we use aggregation with a group by, we are going to have multiple result sets, multiple rows in our result set, one for each grouping. Kind of what we're asking for, and SQL allows you to do that. So think about that's going to handle what you've given it logically. So here's the grouping example, and here we've got we're calculating the max salary. So you can see easily that the max salary for this group of TAs is $60,000. For the profs, it's $100,000. Pretty straightforward. And I get a result set, one for each row corresponding to the sort sequence changing as I'm looping through all of this data. Other questions on that? Okay, just to make sure I understand, all the salaries from R are dropped. Yes, are dropped when we said select for the average P salary. Yes, you're only going to get a result set that has, if you do one of these and look at the whole table with no group by, you're going to get one row. You're going to get a result set of one row. You could have multiple rows. You could have an average salary, average something else here, or a count of the number of cars or whatever it is. So you could add multiple things that come out related to the, in this case, joined relation. That's our intermediate result. But yes, we're only going to get one row when we use this at the highest level at the select statement. It applies to the whole table. One row of data and multiple rows depending on what attribute we've chosen to group by, corresponding to the number of times that value changes in our intermediate or result set. Okay, does that answer that? Why join the registry table if only looking for the salary attribute? I don't think it was a good idea. It was just an example of the kind of mistake you can make, Matthias, and not a great example. I agree. I just wanted to probably show you an example without introducing a new set of tables for you to be paying attention to. The idea is if you're doing joins, that the join is going to execute first before the aggregation function. So you have to keep that in mind, and we'll get to that a little bit later. So just trying to illustrate that. Yeah, it's probably a dumb way to do it. It's wrong. It's probably not what you expected. However, when you look at the SQL, it looks perfectly logical. So it's really not until you understand the order in which things are done in SQL that you're going to figure out that you made a mistake. SQL is going to go ahead and execute whatever it is you give them to execute. All right, let me see. I believe it was okay. If you wanted to do it that way, Patrick is probably correct. Okay. You can group on multiple attributes. So here we got the max salary. And well, let's again look at how it's organized. What we did here is we did a group by name, by job and by name. So that sorts first by job, and then within the job, it sorts by name. I'm not sure that that result set reflects that. I would think Allison would sort before Jack, and Dan would be sort, maybe they're sorting descending. Try to ignore that. I didn't notice that until just now. I'm using somebody else's slide deck. So that's necessarily right. But basically sort by job and then sort by name. Now, if within, often this is an example of something where you're adding something to the sort key that really is a unique attribute within the group by, within the group. So they just get sorted by that attribute. But that does allow you, and this is important, that allows you to pull the name for the people from that table. If it's not in a group by statement, you cannot reference it in the select statement because it's dropped otherwise. So one of the ways of getting this other feature that you really don't care about the max salary of, the max salary for any name is going to, however, to be that max salary. So here's the problem with, I want the name of the person with the maximum salary in that group, and that's not the right query to get that. Do you see? Because we're pulling the name, we're also pulling grouping by name. We're getting every name. And the maximum salary for every single row is the salary for the person in that row, since there's only one item for each. So again, SQL will execute it, but that's probably not the query you were, that's probably not solving the problem that the query that you were asked to solve. The query would be something more like in the problem stated out in terms would be, would you give me the name of the person with the max salary in each group, each payroll group, or each job type? That would be it. And this query is not the answer to that because of what we said, because name is going to pull each row out of the grouping. If we got two people in the same job named Jack, yeah, then we would find the maximum. This query would give you the maximum salary of people with the same name in the same job type. Again, probably not what you were asked, but that's how it would work. SQL is going to execute what you give them to execute. Here, in fact, we're probably not pulling the right thing. So to answer that particular query, what is the name of the person with the maximum salary for each job type? We can't use this query. So we're going to be learning how to get to that. How are we going to make that work? That's called the witnessing problem. How do you pull that in? Not so easy. How am I doing on time? A little bit. And just to add more to the mix about having is the ability to put a selection on the grouping that you've created, the aggregation that you've provided. So here we're doing a group by job, and having is like a where clause that applies to the grouping, not to the overall selection. So here, having minimum salary greater than 80,000, that's going to create a result set where, in fact, you're only going to get one result, one row, because after you do this grouping, you'll have no rows that have satisfied this having condition. And of course, it will give you the right row for this condition, but you'll lose all these because no one in that group will meet that condition. Just showing you how it works. Whether that was what you wanted is just to find the profs or not, people who have more than 80,000. But when you ask for that in the having, you're going to throw away groups where the maximum salary is. And notice that is less than 80,000. And notice that minimum here, this function is pointing not to it's pointing to the maximum salary for the selection, not the minimum salary for any one particular row. So it's the maximum salary that's retained for the grouping, and that's where the selection is done. Again, in this case now, the order in which this clause is executed matters. And this is an example of that. Again, is that what you wanted? I don't know, maybe it was, but that would eliminate everything except the one row. We have two groups here, but this group does not meet the having clause. Doesn't have a row that meets that. So that all that data is going to be gone, and only data from this grouping is going to be persisted. Okay. All right. So all of your questions are about, well, how it can be answered if you understand how the aggregation is processed internally. So let's go through that a little bit. So here's our query. Select job, and I want the max of the salary. I'm just looking at one relation. I'm looking at one table by payroll. I'm aggregating that by job, and I'm applying a selection criteria on the aggregation. So let's look at how that works. The first thing we're going to do is do the aggregation. And the aggregation is going to involve calculating the maximum salary. And we're calling that max sal in our expression. And we're going to calculate the minimum, which it really is, we're going to call a min sal. So we're calculating both a max and a minimum, because we've got max minimum here and we've got maximum up here. So that is done on the initially on the entire relation. That's the grouping. Grouping and the having applies to the entire relation. That gives us, when we execute that, we get the TA, we get a max sal of 60, we get a min sal of 50. For the prof aggregations, we get 100,000, we get 90,000. That's all we have to work with. Now we're going to apply this min salary, which we computed from here, which is a selection. That's what this means. This means, I think this is gamma, and that stands for aggregation. And this is a sigma, stands for selection. And it's the same symbols used for a where clause, by the way. It's also a selection of sigma in the relational algebra. I know the terminology is a little confusing, but let's get onto that a little bit. So this is going to be applied to this intermediate relation that was generated, and that's going to result in that that relation being pruned, because this row does not meet that condition. This is the only condition that's left. This is the only row that's left, I'm sorry, after that condition has been applied, and we're going to do our selection out of that. And that gives us, whoops, I went too far, the final answer. So that's how this answer results. And what's going in the projection, ooh, I would have thought we got that. The projection should have shown us, just job and the max salary, job and max salary. This min salary is not reported anywhere because we didn't select for it, so it should go away. We've dropped it from the result set. That's how this thing gets built up. There it is, finally, where we do just the two fields. Sorry, somehow that's a little bit confusing there, but that's the order in which that happens. That the aggregation occurs first, then the having is applied, then the projection is done on the result. And in general, we're going to see the rules for that. If we look just at the relational algebra, it looks like so. It looks like this is our from. This is our from table. That's at the bottom always. From is at the bottom. Then we do the group by. Then we do the having, and finally we do here the selection. It's called projection. Which particular fields out of the relation do I actually want to report up? And this selection is the same, use the same symbol as an operation is used by a where clause. It just depends. The where clause is applied here at the first step. This selection is supplied, if performed after the aggregation occurs. And in general, then we've looked at select, from, where, group by, having, and order. And this is our vocabulary summary. And this is the order in which it's processed. Is the first thing that happens is that we look at the tables, and that's processing of the from, and which references which tables we're looking at, and anywhere selection that's occurring. So that's the select part, any joins, that happens first. The next thing that happens is aggregation. The next thing that happens is the having selection, aggregation, the selection on the having groups, on the groups. Finally, you have something like sorting. The order by would occur when you finally have a result set. Then you get the projection, and you could even do eliminate duplicates with something like a keyword like distinct. That's the order in which these things occur. And that order matters for how logically your query is going to be processed. This comes down to, and I think I'm going to finish up there and take a look at your questions, is this FWGHOS. I don't know who trademarked this. That, if you look at the clauses in a select statement, in a SQL statement, select from, where, group by, having, order by, from, where, in order, in sequence, they are processed from, where, the grouping, the having, the order by, and finally the select. So that's the order in which they occur. And that's why you got the results that you got from executing various of those queries. All right, I think we're going to talk about the witnessing problem. We'll never get through that today. If you think this raises a lot of questions, wait till you see when we go to witnessing. We've got to solve this problem. How do I get the name of the person with the max salary? And that's called the witnessing problem. All right, let me see if we need to take some questions here. In the example, oh, Josh is writing that. Okay. Anything, you guys? You guys got everything in control? Anything I need to answer? I don't think so. I got another message down here. Anybody want to talk? Is this always the order? This is always the order in which a SQL statement is processed. This is how it's done. F, W, G, H, O, and S. From, you get the tables. Where, you do selection on the tables. Then you do the group by, you apply having to the group by, because that's what having does. Then you do sorting, and finally you do projection. You do the selection of the columns that only the columns you want to see. You might have seen already in your homework, select star. I just want them all. But if you're looking at very, very large tables, you're going to get a lot of columns. So you just get into a habit of writing a select that just references the columns that you care about. Okay. I think we're done for the day, unless I'll let the questions go. And then I'm going to go offline, go to the other meeting, but I'll let these questions run a little bit. Good luck with the homework. You're unless you join the class late, it's due tonight. And the second homework is ready for you to start on.